Thank you for your attention for my oral presentation. And in my work, I'm most focused on how to apply the microwave assisted heating in reaction and compare it with conventional heating. So as we all know, there is very different from the conventional heating and the microwave heating. The heating way is so different. In microwave heating, we always set heat from the material inside and diffusing the heat to outside. And it's very different with conventional. In conventional oven, it always heat all the room inside and make the catalyst in a high temperature. So in this case, microwave can achieve very different benefit in reaction, such as just select. We have highly selectivity, just heat the materials we want, and the hot pot can increase temperature very sharply. And in this case, the hot pots exist and can enhance some the reaction rate and also makes the reaction with a higher conversion rate. And in this work, we choose the ethanol as a raw material, and under reaction, we converted dehydration then to ethylene. And then in this case, there is two ways to reaction occurred. One is in high temperature with ethylene occurred, and in some lower temperature, the ether will occur. And in this case, the very important thing to choose is to choose a suitable catalyst. A very strong acid is a good choice for them. In this case, we use HBW. This acid is very strong and it can easily make the reaction occur. And in other side, HBW, because the toxin exists inside, it can have a good reaction, reflection with impacted by microwave. So under microwave irradiation flux, the temperature will easily can increase a higher temperature and make the reaction occur. But it is not good for the structures because HBW is a cluster with tungsten oxide and oxygen and fluorine. And in high temperature, the structure will very easily to destroyed and lose the chemical properties. Turn to tungsten oxide, even it can have a good properties in microwave heating, but it's not good for the reaction occurred. So in this case, we needed to choose a good support to diffusing the HBW on the surface, and in this way, it can make it more stability. And in this case, the support cannot absorb the microwave too much, so we choose silicon oxide. One of the silicon oxide use SPA50. So this material is has a very large surface, and the channel is very crystal. So we use the impregnation way to doping the HBW into the SPA50. So with the impregnation, we control the doping concentration with HBW from 0.1 to 0.4 or some more high doping concentration. And by circling in this way, it can be easily controlled with the doping concentration. And we wanted the HBW just attached on the SPA50 channel's surface. In this way, we can provide a more catalysis site. And the B shows the system we use just with nitrogen gas with 100 ml per minute and through the ethanol and to reaction. We test by GC and FTIR. And here is a figure with steam we test. Figure A is a pure SPA50. And as you can see, the channel is very smoothly and there is no other things inside. And the figure B is after we doping HBW, you can see clearly some channels were filled by HBW. And the figure C is more highlightification of the figure B. And when we take EDS, we can see toxin is all around the SPA50, not only the field side. So we think, and with the high modification with HADF, we can see some height spots under the canal surface, and it shows HPW is not only filled by the canal, but also in the canal surface. And XRD shows there is some tiny peaks with HPW. There is no change. This means during we use the impregnated way, HPW, the structure has not destroyed by with synthesis, still keep the HPW clusters inside. And in case we compared with microwave heating and conventional heating, the key points is to test the real temperature with the catalyst layers. So we use a fiber detector to insert the catalyst layer and test record the number with a fiber detector and also IR detector temperature. So in this case, we can simulation one line to correct the IR temperature we get, then we get the real temperature in the catalysis layer. And in this case, we do the different heating property with different doping consideration with 0.1 to 0.4. And as you can see, around the 10 watt to 50 watt to 20 watt, the temperature with catalysis layer almost in 115 centigrade. And with this microwave power, we just test the conventional rate and the selective rate with SNI. As you can see, with 0.3 gram per gram has the best shows maybe just from the 50 watt, 20 watt is good than 0.4 gram per gram. That's we thought over doping consideration under the reaction, maybe it will fill the canal, and in high temperature, the HPW will ruin, destroyed, and lost the chemical properties. It's not good for that. So in this figure, we use the 0.3 gram per gram to test compared with conventional heating and microwave heating. And with microwave power, we just 2 power gap and to test the conventional rate gas consumption. As you can see, at the beginning, the low water and with low temperature, the main gas consumption still ethanol, and some of is ether. This is a less ethane occurred, and after the temperature with high power, with high temperature, around 60 watt, the gas consumption is almost ethane. And the temperature is just 146 centigrade. Compared with conventional heating, over 200 centigrade with conventional heating, the reaction can almost be ethane. And compared figure C and D is this different reaction way we tested by FTIR. And figure E is compared with other works, not only with HPW, but also with some other catalyst, and compared with conventional rate and selective rate. And as you can see, our work is with the lowest temperature and with a very high conventional rate and selective rate. And here we just test with the circling to prove the sustainability with that. After circling test, the ethane still stay a high level with it. And we compared the catalyst before and after. We just can find some CH2 bond and something in it. The HPW is still exists. And here is we compared with different heating process and different doping process. As you can see in microwave heating, with 0.4 gram per gram doping, after preheating, the catalyst color is almost no change. And after reaction, it will turn to deep color, there has some cooking and structure destroy can occur. Compared with conventional heating with 0.3 gram per gram, the color turns to yellow. That's we think thought that with some cooking occurred in the surface with SPF covered with HPW and SPF 15, and that's obvious. And we also tested ramen. We also tested ramen before and after. Before ramen test, there is no change before reaction. But in after reaction, it's hard to test with that. Just the ramen rays focus on the material. It just turn to black. And the ramen peaks shows the toxic oxide and the carbon was all shows, just can see it clearly. And with the experiment the data we got and some previous study, here is the reaction step with this reaction. As you can see, there is two ways to get the ethylene with step 1, step 3, step 5. And another is just absorb to ethylene and to step 4 and to step 6. These two ways can occur the ethylene in high temperature, and diether occurs just with two ethanol absorbed and will release a diether. So based on this, we just do some DFT calculations based on CP2K. And because HPW has 3 very strong acids with 3 hydrogen atoms, so put in different area, as you can see in figure A first. And the 3 different hydrogen atoms put in different area from the outer edge to interface. And we calculate the different position to absorb the ethanol. And we found also not only ethanol but also ethylene as oxide in different in these 3 different positions. So we found from interface the ethanol is more easy to absorption, and the ethylene and the ethylene ester is more easy to release on the outer edge. So in this case, we can control after we put the HPW into the SPA 50 surface. It is more easily to find dehydration the water in interface and release the products in the top outage. So in this work, we just use the HPW doped in SPA 50 and make a high conversion rate with ethanol and also high conversion rate with selectivity with ethylene with a low temperature compared with conventional heating. And after we doping it and in low temperature, we can make the HPW more stability. And by the mechanism, we found the interface is more good benefit for the reaction occurred. And that's all the work. Thanks for your attention.
Thank you. Thank you very much. Very interesting work again. And any questions? Yes, please.
Thank you for the talk. Based on what you said, I understand that while performing Raman spectroscopy of the used catalyst, you see some black color formation on the surface.
Yes.
This is because of carbon.
Yes, it's carbon.
Where is this coming from?
Because we test the catalyst after reaction.
Mm-hmm.
So in this reaction, we just with ethanol to ethylene. So ethanol has 2 carbon inside, and there is some not only ethanol but also some ethylene we cannot release, or some not pure catalyst, but also the in catalyst, because SPA 15 in canal, it can also absorb some ethanol or some middle, some ethylene or something else in it. So in ramen, some of the products, middle product, were also observed in HBW. And in this case, ramen's energy is very high, and it can ruin the HBW structure, and also make this a soft carbon, a soft middle products turn to carbon. Yes, I think about that.
Okay, and can you please take your DFT slide?
Yes, you mean this slide?
And here you see it's C4H10O, adsorbed species. That is what you mean?
Yes, and I mean just ramen turn black, and all this situation may be in that.
So I mean, my question is that this means that carbon-carbon coupling take place during the reaction.
Sorry.
C4, where this C4 carbon molecule came?
Yes. Sorry, I can't follow you.
You see, C4H10O.
C4H10O
Yeah.
is one of the middle.
You mean
yes.
intermediate? Intermediate?
C4H10O is occurred in low temperature. So as you can see, we in our the DFT not only calculate only one way to occur the ethylene, but also one way to C4H10O. This reaction may be occurred in low temperature. This reaction occurred in low temperature, not so higher temperature in it.
Okay. Thank you.
Okay, any questions? Any more questions? Okay, perhaps one from you. Can you go back to show